Okay, I'm gonna go over the charge tutorial. It's possible you're gonna hear this Juventus versus Bologna football match. I'm also watching. I didn't feel like wearing my headset to do this, but anyway, this is where we had the scotch tape, and we did different things with it. So if we take a piece and stick it at the table, pull it off, let's see, objects are attracted to anything we bring it up to. And if we bring a second piece, we prepare it in the same way. That's the important thing here. You prepare it in the same exact way, they'll repel. Keep your hands and other objects away. Explain why this is necessary. Well, since we're trying to learn about charge, it's a pretty stupid question. But what we do notice if we touch it with our hand, then they lose their magic. They don't do their thing anymore, which I don't understand because let's see, peel it off and hang it from a wooden dowel. Okay, that makes sense. But if we held it by the end, it would work still, but it would slowly lose its magic. But that's just an observation. That's not telling us exactly why it's happening. Distance between the tapes. They get closer, they react more strongly. Okay, so now we have a case where we prepare the tapes in different ways. Once is we pull it off the table, and once is we pull it off of each other. And so we label one the top and bottom before we stuck them together. And since the two tops are prepared the same way and the two bottoms are prepared the same way, we're not surprised if they repel. And then T and B are prepared different ways, and by chance, so far, we don't know anything about what's going on, but by chance, when they're prepared different ways, they attract. It's not necessarily true. We just know that if they're prepared identically, they'll repel. It's not always true if you prepare them differently that they'll always repel. It depends on the triboelectric table. Well, the two materials you use, in this case, tape and wood or tape and tape, and then we need what's called a triboelectric table, which I suppose I should get that, because not everybody, well, if you're in my class, you saw it, but maybe somebody else will look at this. Hold on, I'm going to pause. Okay, may have jumped a little on you. So notice that I hadn't put it in the module. Now it's there. It'll be there in future. So you use the triboelectric table, and you pick your two materials. So we have wood, and let's see, I forget, is saran wrap, scotch tape. Here you go. So pull scotch tape off surface and it will become charged. Well, yeah. So it says here that wood is more negative. Okay, so then if I pull the tape off the table, it'll become positive. And then the other thing is the glue. Okay, it mentioned the glue part, but this is not a complete table. I guess I better get the complete oh, here we go, most plus charges. So somewhere is going to be the glue of the well, it's not there, but anyways, you would be able to, if we had the right triboelectric table, then we would see how this is set up. But the point is that just because two things are prepared differently doesn't guarantee that they could attract. They could still repel. But if two materials are prepared in exactly the same way, they're going to repel. Okay, to compare, one tape, yeah, if I get the rod, rub it with wool, we notice one tape is attracted and one tape is repelled. There isn't a whole lot you can tell. And then the very next question is it possible there's only one type of charge? Well, I would say no, because we observe two interactions, repulsion and attraction. And so, but there's three different materials. So in fact, there could be three charge types. And so that if I say that two tapes are each one type, I could have a third type that's attracted to type one of the two and repelled of one of the two. But the simplest explanation that there's only two types, especially because we do it by rubbing things together or pulling things apart. So Occam's razor says the simplest explanation is the best. In this case, there are only two charges, so that's the best we can do. How do you tell if two objects are positively charged? How do they charge? Well, two of them that are positively charged repel. We know that the 2T or the 2B repel. So anything repelled but one of the T or B, let's see, T is repelled, B is attracted to the rod, so we have to conclude that it's the T is anything attracted to the rod is negative, and anything repelled by the rod is the same charge, positive. I mean, if they're attracted, we could still argue that there's a third type of charge. Yeah, that's the discussion with the instructor. Yeah, so part 2 is about linear superposition, which is profoundly important to our world. And it just simply means that if I want to figure out the force on a charge from more than one charge, I can just calculate the pairs of charges by themselves. We don't have to make a special rule for more than one charge. And also it says here that the force is proportional to the one charge times the other, divided by the distance squared between them. Okay, so two positive charges, the magnitude of Q is greater than capital Q. So F of Q from capital Q. So I guess this is, I got the nomenclature reversed here if I think about it for a minute. It doesn't matter, you just have to define it. I don't think there's a convention for this. So we want F of capital Q on little q, F of little q on capital Q. And they're equal and opposite because Newton's third law, that's all there is to it. Plus, if you look at this, there's no, you just plug in the two charges and the distance between them. So it means that, there's no ordering. This is a simple equation. It's not a vector equation. Other than this is a vector and you would have needed an r hat, but Coulomb's law by itself is not inherently a vector equation. You have to add the r hat. Okay, if I double the distance, since I'm using the distance 1 over the distance squared, you see I end up with a 4 here, so it's 1/4. Let's see, 2 or more. Yeah, student 1 is mostly correct. They should have said that it's, well, let's see, yeah, 3 times as large. Well, I know it says here that they're all the same distance away, but in fact, it's not 3 times as long. The student is mostly correct. 3 times stronger is, yeah, it's not exactly correct. That's right. So I guess I need to get rid of that. Oops. So you could be fooled into it because the distances are all the same. But if I put a positive Q above here, big Q, the same exact distance, and the net force would be 0. Okay, so I made a mistake. Direction of the net force, assuming that the two angles I labeled here, theta 1 and theta 2, are equal. That means with symmetry arguments, the net force is straight up, and plus Q, and these two, the one on the left will have some rightward facing horizontal components. This one will have some leftward facing, but if we assume the two angles are equal, those horizontal components will cancel. What if you said about okay, already answered in B1. Well, that's not true anymore. But I just finished the magnitude on the, oh wait, B1, which is on the part when the two are added. What if they have the magnitude on the, it is not completely answered in B1, but it's answered in both B1 and B2. So it's going to be stronger, just because of the way they're placed, but you have to be careful. It's not simply stronger because of the existence. They just happen to be arranged so that some part of each one of them adds together. So it's not that stupid of a question. Okay, so rank them. Now, I went through it, and it took me a little while to come up with the right answer, but it would be case D, because I said, all right, this is the size of a 3Q vector. This is the size of a 1Q, so about 1/3 of one of these things. So this has 3 of them, but it's this one here because let's go over here. See, all 3 of these are equal. And the horizontal components cancel. You get left with a net here. Now that's still 3Q. Now in this case, all 3 of the components, they're 3Q altogether. Let's say, well, there's 3 of them on top of each other. So that would mean then there's 3 contributions like that, and they add up to the total. And then here, though, these two are a little bit smaller. So this one here will be smaller than, so C will be smaller than A. And then in this one here, it's pretty easy to draw the resultant. And with 3 and 3, you see that this one is going to be the square root of 18. Then let's see, that one's easy. Let's see if we can get a sense of it here. Now we don't know these angles. So, but anyways, you can just look at the components and the angles, and then you can figure out it's D is the biggest, B is the second, because it's just from one point. Yeah, by definition, this one has to be bigger than A and C. So A, B, and C are easy. Well, relatively easy, but it's an easy argument because here all the components help each other. Here in both A and C, the two side components have horizontals that fight with each other. And but you see here, these two distances are longer. So these two components are smaller, even if the thetas were the same, as opposed to this case over here, if it would, right like that. So then that would be closer. Okay. What's next? Yeah, this is a long one. So what happens if you charge up a rod? So if you bring it close, it's attracted. If they touch, then all of a sudden they'll repel. And you may not have noticed that because it depends on the humidity that day, and the air conditioning was pretty bad. So in the fall semester, it's harder to do. In this case, hold it horizontally. Now I'm looking down at the pith balls. So I basically see them all kind of, the repellings would be about the same if I keep the distance the same. The ones here at the end might be a little smaller because the parts of the rod that yeah, so this would be smaller also. And because the parts of the rod from way over here aren't helping as much. And then further away, there's less. Close to my hand, there would be less because charge is going to bleed off into my hand. And the charges, they do, even though it's called static electricity, the charges will slowly migrate around, distribute slowly. And then, as I said, my hand will bleed off charge. And okay, if I rub it in a way that I get it in just like at the very end of the rod, and if I'm quick about it, you'll notice that it does behave sort of like a point charge. But in general, it won't because the charges will slowly distribute. So you may have observed something that made it look a little bit like a point charge, and that if you wrote that down, well, at least you need to really explain it. You can't just write it down. You have to say, this is, if it was a point charge, then and it was here that near the end, then I would notice that distance away from the end would matter instead of simply distance away from the rod. So you'd have to say that. Two rods next to each other, whether would the one further apart exert a force? Well, if they're both charged the same, I don't understand. I guess because students think somehow they cancel each other. I don't know. I think it's a dumb question. Why not? But anytime, the way you do this is like in calculus, you just pick pieces of the rod. We call it a DQ because we know there's a charge on the rod. So you pick some small volume or area or length, depending on how you define things, and then each DQ then contributes to the test charge, like here. Just the same as any other two pairs of charges. They're proportional. DQ times the test charge divided by the distance between their centers squared. If I move one rod away, then the deflection will become less, but it won't go to zero because the remaining rod will still be exerting a force, an influence. This one was a little hard to understand the way it was written. But we can, you can, this is the idea of the DQs, where I divide up the rod into small pieces, and then I can basically take the center of it. So if they're both positive, which I think is what it said, then that's the red, and then this is closer, point B is closer. So this red is larger than that red. If I want to talk about the net force on the whole thing, then I just pick the centers of all of them. And so now I have segment 5, segment 1, segment 2, 3, 2, 4, and segment 3. They all contribute, and their components are longer and longer because I'm getting closer and closer. And similarly here, but the contribution from 5 is the biggest, then 4, then 3, 2, 1, because they're just getting further away. And then I add them all together to get the final result in this cyan color. Does segment of course it does. I mean, that is the whole basis of the principle of superposition. I don't know how you would explain it, but because you don't have any way to demonstrate it. But it does. It has to. Because if it didn't, then it would contradict what you observe in the other two pictures, and you can't, that can't happen. Okay, let's see. Right, this is sort of synergizing the everything up to this point. You get less deflection, and if it was a hanging pitch ball, but you get less force between the two, the rod and the test charge, or the 2 point charges, because the parts of the charge, just like above here, well, 1 through 5, the parts near the end will contribute less because they're further away, and they have partner matching. Any piece I pick on the right, I can find a matching piece on the left. And the horizontal components will cancel each other, so that would mean that the net force is going to be less. Oh, here, this one is interesting. This is a kind of way to model what happens when I bring a charged object, like the charged rod, up to the pitch ball. and the pith ball is got the silver paint on it, the metallic paint. But in this case, you have this weird ball that's negative on one side and charged and positive on the other side. So if I bring the positive test charge close, both sides of the ball will contribute, the positive side and the negative side, but they'll be, say, to here and to here. And I guess we should use a different color for here. So there's an R to the positive side, and then there's an R to the negative side. And when you're close, the difference between them, 1 over R positive squared minus 1 over R negative squared, will be a significant fraction. So the difference divided by the let's see, the difference divided by the average will be and times 100. If it's greater than 10%, then you would see an effect. As you get further and further away, because the R is on the bottom, the difference between them will become so tiny that you won't notice any difference, and the two charges will effectively cancel each other out. Is it consistent with Coulomb's law? Well, of course it is. It's the only way I can explain it is with Coulomb's law. A dumb question. I really don't get it. But I guess the point is, your answer would be no, and the reason is because I use Coulomb's law to explain it. It might not mean I'm right, but if I use Coulomb's law to explain it, then it has to be consistent. Hanging on charge from 10 charge, describe what you observe. Yeah. So I've had the metal ball, the little pith ball with tape. We've already observed that it's attracted at first. And then why does that happen? Because, and it's part of a pre-lab in my lab classes, but if I bring the positively charged tape nearby, then what happens is negative charges are attracted here and they migrate away, and then you're left with a kind of net positive on this side. And so now they're attracted, and this is called polarization. Polar, right? Because it comes from creating a north and south pole. Now we're creating an electric polarization. So you get a negative and positive end. That's all. All right, 23 minutes. That's a long tutorial. We didn't get it finished. I remember in my class, my charge section, in my activity section in fall 2022. See ya.